Hey everybody, how's it going? Welcome to class in my office. Uh, Today we're going to talk about moments. We've finished up chapter 3, chapter 2, taken the exam, and now we're moving on to a new section. So chapter 4 is all about moments. Some of you may have heard torque before, okay? You can kind of think of these as pretty much the same thing. To talk about moments, I've brought this bar with me today, okay? So you can look at this. This is a bar that I've used for a lot of different things. It's pretty heavy duty. If you look at the thickness or the gauge on the steel there. I've marked a couple lines along this bar, and I don't know if you can see them very well, but I have a line right here, and a line right in the center, and then a line here at 1/4 the length. This bar, if I remember right, I think I wrote on it once, its actual mass, but it's about 16 pounds if I remember right. Pretty good heavy duty bar, okay? This bar, I want you to think just really quick as you look at this bar. If you had to hang on to this bar, how would you hold it? For me, if I had to hang on to it and keep it horizontal, I might hold it like this. And it's not too bad to hold it like this. I think I could do it for quite a while. Now, if you ask me to hold it here at 1/4 the length across, I would hold it, and it's not too bad still. It's weighing on my wrist a little bit more. Think about why that is. Why is it harder for me to hold the bar here than it is here? I'm still holding up the same amount of force or the same amount of weight because this bar is still 16 pounds. But when I hold it right here at 1/4 the length, I have to really twist my arm. And if you ask me to hold it at the very end, oh boy, I don't think my wrist could do this for very long, and it just wants to fall down. But holding the bar like this, I feel even more rotation and twist in my wrist trying to keep this thing horizontal. And I don't think I could do that longer than, I don't know, much longer than I just did. But from the middle, it's pretty easy. So why is that? Why is that so hard? That's what moments are, okay? As you consider what's going on, and even if we were to draw a free body diagram, as I hold this up, the amount of force in the y direction or vertical has to overcome the amount of weight in the bar. And that's true whether I hold it in the middle or hold it from the side. Maybe let's draw both situations with a free body diagram, and we'll just consider some of the differences. So here with this whiteboard, I'm going to sketch one scenario of the bar, and I hope that you can see that okay on the screen as it's shown. And then here's a second scenario of the bar. I'm going to put it just a little bit lower. Now the bar has weight, and we could say that pretty much the whole weight of the bar acts right through the middle, okay? So it's like the weight is coming down here. If we were to express it with one arrow or one vector, we'd say, hey, here's the weight of the bar coming down. And that'll be true for both situations. Now, for the top situation, let's say I'm grabbing the bar with my hand and pressing right up in the middle, right where this, we could say the weight acts, okay, right through the center of mass. And so I'm exerting the force Kyle, okay, we'll say, at the same location that the force is coming down. However, when I move my arm out along the length of the bar, it's as if I'm putting that force right here. We'll call that force Kyle. Okay, again, at 1/4 the length from the end or 1/4 from the middle. And also, the magnitude of that force is still going to be the weight of the bar. We could do some of the forces in the y direction. We know they're equal to 0. It was in equilibrium. And we could say 0 equals negative Fw plus F Kyle. And we could compute the force of each of those. There's no other y direction force here, and so I think we're pretty complete, and this line works for both scenarios. So why is it then, if the force I exert is the same in either situation, whether I'm holding the bar from the middle or from 1/4 the distance? Haven't tried it like that, but the amount of force that I apply upward to keep this thing suspended seems to be the same. So why is it that I can't stand there for very long? It's the rotation that I feel, right? So it's this tendency of the bar to rotate downward. And see, I'm pushing up on this, but it's still, I have to like counter rotate the bar to keep it steady. And you could hold anything in your hand and experience the same feeling. Likewise, as I hold this, I have to counter rotate to keep this thing steady. So what's causing me to feel rotation? It's that there is space between the force that's acting here and the force that I'm holding it up with. That space or distance that's perpendicular to the force is creating a moment, or you might think of it as a torque. We're going to call it moments in this class, and it's causing rotation. And so to keep it in steady, what I have to do is apply M of Kyle. Okay, moment of Kyle, okay? That's the twist in my wrist that I'm applying to the bar to keep the bar steady and to keep the bar in equilibrium, okay? So that rotation, that moment is required to keep this bar in equilibrium. Otherwise, it's going to rotate downward if I only apply a vertical force. So I apply that moment. Now what's the quantity of that moment? We can find the quantity of that moment if we will look at how much is required to keep this force in check. A moment in the scalar method, we'll say a moment is computed by taking the force multiplied by distance. And I'm just going to make a little subnote that tells us that that is a perpendicular distance. Okay, so the perpendicular distance to the direction of the force, that computes our moment. And like we just barely said, for this bar to be in equilibrium, we must have all of the forces sum to zero. And likewise, you can think of it as all of the moments must sum to zero. And so as we look at this situation, let's sum the moments and say sum of the moments equals 0. And then the next line I will write 0 equals, and let's write all of the moments. Now, M sub Kyle is the moment or the rotation that's resisting the rotation of this bar that's in my wrist. And because it's going clockwise, I will say that it is a negative value. We'll talk about positive and negative in just a minute. Now, this force here is about this point of where I'm applying my Y force. It's a counterclockwise rotation, so I'm going to say it's positive. So I'm going to say plus the force of weight times by the distance d. Now to solve, if I know the force of the weight and I know the distance d, I can bring the moment of Kyle's wrist over to the other side and have a quantity there. Okay, so again, that's pretty simple for us to solve. Now moments, as you think about it, what will the units be for a moment? Well, we've got either pounds right here or newtons. Okay, and for distance we're going to have feet or meters. So we're going to say that units for moments will be either pound-feet or Newton-meters. Okay, is our two unit methods that we'll probably lean on most of the time. And we may need to convert units as necessary to make it all line up. But you get the gist of it, or the hang of it. Now, I said we'd talk about whether it was positive or negative, and let's do that right now. As you get into moments and in statics, there's something called the right-hand rule that we'll talk about. And the right hand rule helps us understand whether values are positive or negative. Now, I'm just going to look at how I drew this curly arrow, and I'm just going to curve my right hand fingers in the direction of the arrow, and my thumb goes into the board. That indicates a negative value. We'll say moments are positive coming towards you and negative going into the board. And I will say that a moment is a vector, and it's a vector that's perpendicular to the direction or moment arm as well as perpendicular to the force. That's why you see it here coming out or into the board. So, like I said, I curve my fingers around that curly arrow and I see that's a negative moment. I can also say, okay, well that was negative. That must mean this is causing a positive moment. If I go from the point of rotation and start my right hand there and then curve my fingers down in the direction of the force along the line of action of the force, my thumb points out towards you. So my right hand indicates that going from the point along the moment arm and then curling in the direction of the force, my thumb should point in the direction of the moment, which in this case is positive. In this case is, for the moments of Kyle's wrist, it's negative, and it's positive for the weight of the bar. Okay, and so that's how we'll define positive or negative moments for right now. Now, as you look around you, wherever you may be watching this video, I'd like you to think about the things around you, and I want you to hold something up and think about the rotation or twist that you feel in your wrist, and think about what is required to maintain that in equilibrium. And like we just explained, you should think of two things. So pause the video for a minute and think about those two things that are required to hold something in equilibrium when you don't hold it from the center of the bar. Okay, I hope you were able to pause that, and I hope that you realize that just like with this bar or whatever it was you were holding up, you need to have a force as well as a moment or a rotation to resist that and keep it in a state of equilibrium where it's not accelerating. Okay?